Let's look at this problem here. We have that the radius of a circular oil slick on the surface of a large body of water is increasing, so the radius is increasing at the rate of 10 feet per minute. Now, there's that word rate. So what do we think? You see that word rate, what do you think? As soon as you see rate, you think derivative. All right, so what have we got now? The radius of a circular oil slick on the surface of a large body of water is increasing at the rate of 10 feet per minute. So you can imagine there's this circular oil slick, and the radius is getting bigger by 10 feet every minute. So in 1 minute, it's something, and 1 minute later, it's 10 feet more. Now, what we want to do is find the rate, the derivative, at which the area of the circle is changing when the radius is at 8 feet. All right, so right when the radius is 8 feet, find the rate at which the area of that circle is changing. So let's start here by drawing a picture. So I'll draw a circle, and then what we'll do is we will label all variable quantities. So what's changing here? We've got a circle, and we're told something about the radius. All right, so the radius is changing, right? So I'm going to label that. So here's a circle. I'll put the dot at the center, and I'll draw a line out here, and that'll be the radius. And what else is changing here? Well, what have we got? Find the rate at which the area. Okay, so the area. All right, so this circle is going to have some area. Okay, so I've labeled the variable quantities. And now what I'm going to do is I'm going to write what it is that I have and what it is that I want. I think it's a good idea to every time you do these problems, you write down what you have and what it is you want. Then it's all right in front of you. So let's see, what do we want to do? We want to find, all right, here's what we want to do. We want to find the rate, so I'm going to write a derivative, the rate, dA dt, find the rate at which the area changes when, now here's what we have, dr dt is equal to, all right, let's go over and find out, what is dr dt? Well, we're given that the rate of the radius, all right, the radius is increasing, right? The radius is increasing. So do you see this? It's dr dt, right? So you got a minute on the bottom. That's the time. So I'm going to have a dt on the bottom. And a feet, that's a radius. So I'm going to have a dr dt. So back over here, dr dt is equal to what number? It was a 10. So I'm going to write that, and I'm going to use the units. 10 feet per minute. All right, so find dA dt when dr dt equals 10, and we also know we want it at r equals 8 feet, and that's coming from the bottom, way down here, the last sentence. Find all this when it's happening right at 8 feet. All right, so next up, let's get an equation that relates both A, right up here, A and R. Okay, so what are we dealing with? We're dealing with the area of a circle. And we just happen to know this one, right? We know that the area of a circle is equal to pi r squared. Now, let's differentiate. All right, with respect to t, right? I don't want to find, I'm not doing this. I don't want dA dr because a is a function of t, r is a function of t. So let's use implicit differentiation, and we will get dA dt equals, now pi, that's a constant, times, okay, what do we get here? Be careful. This is a power, right? So it's going to be the derivative of the outside. So I'll bring the 2 down, decrease it by 1, times the derivative of the inside, right? This is a power. It's a power, so I'll use the power rule. Derivative of the outside times the derivative of the inside. Now, the derivative of the inside, I'm just going to denote that by dr dt, right? The derivative of r with respect to t. Let's fix that up a little bit. dA dt is equal to 2 pi r, 2 minus 1 is 1, dr dt. Now, let's substitute. I've got these values. dA dt, we don't have a value for that. That's what we're trying to find. So we'll just rewrite dA dt is equal to 2 pi times r. Now r, that's the radius at which we want to find all these changes, and that is the 8, but I wrote it up here right at the beginning, so it's really right in front of me. That's equal to 8. Now, I like to use the units because it tells you at the end exactly what you have. So I'm going to have 8 feet times what? dr dt. Now, I know what dr dt is. From the original problem, dr dt is equal to 10 feet per minute. So let's put that in. 10 feet per minute. I'll do this over here now. So dA dt is equal to 2 times 8 is 16, times 10 is 160 pi. Now, this is what? I've got, look at our units here. It's feet times feet. That's square feet, right? Feet squared. So I'll get feet squared, and then I still have the minutes in the bottom. Now look at our units here. This is an area. Look at your units. Square feet. That's an area. So if I write it so it's a little bit more easier to read, I'll just say dA dt is equal to 160 pi square feet per minute. Now, I could say I'm done. Probably good enough. That's exact. Or I could say, pi is approximately 3.14. And if I substitute that value in, I get this. I get that dA dt is equal to approximately 502.4 square feet per minute. All right, so I'm getting this. I'm getting dA dt. I'm really done, but I'm going to do one more step here. What do we get? We got 502.4 square feet per minute. So I've got a number, but I like to interpret it. I like to know exactly what that means so I could tell somebody, explain to somebody what this number means. Now, I've got this fraction bar right here. I'm going to write this whole thing as a fraction. So I'm going to write dA dt is equal to, all right, 502.4 square feet per minute. Now, there's really a 1 down here, so I'm going to write 1 minute. So here's how I'm going to interpret this. I'm going to say in the next minute, from minute, where did we start at 8? From minute 8 to minute 9, the area of the oil slick, I'm going to go back to the original. I don't want to just write circle, although I could, but let's put it in context of the problem. The area of the oil slick can be expected to, now I'm going to say increase, so I'll tell you why for sure in a minute here. Increase by, what do we get? Let's say about here, by about 502.4 square feet. All right, so what I'm saying here is when I interpret this, right, it's a rate, so it's this many per this many. So if I change the bottom here, the top will change by this much. So I'm saying in the next minute, right, if I increase the number of minutes by 1 from 8 to 9, the area of the slick, which is the top number, that can be expected to increase by about this much right here. Now I'm going to say increase. Let's see why. All right, here's our derivative, right? Our derivative is this. dA dt equals 502.4 square feet per minute. Now, if you look at this, we're saying dA dt is equal to, all right, that's the number. That's a positive number. So the first derivative is positive. And the first derivative in positive means that A, go back to the original function, A is increasing. So what we have here is this. You can see it as R increases, A increases. And I know exactly how. I know exactly how it's increasing at 8 minutes.